Hello, welcome back to another lecture. I started videotaping this lecture, but unfortunately, I realized halfway through it that the microphone wasn't working, so I'm not going to erase everything and do it over again. Basically, I'm going to explain it. The problem is we have a truss right here, and in this truss, the load is given. Dead load is 25 kips, life load is 25 kips. And then we want to design this member right here. And this member is basically, they said it's going to be made from two different angle iron right here. I got two different angle iron back to back and for a tension member. And there's a gusset plate between them at the connection. As you know, I just did a YouTube video on how to design the gusset plate. Look at that one, which is okay. Design this member, and this is what we have been given. First thing we're going to do, we're going to go ahead and calculate the reaction. Well, no, I take it back. First thing we're going to do, we're going to calculate the load per LFRD, which PU become 1.2 times dead load plus 1.6 times life load. That became 70. And because it's a symmetrical reaction, is 70 here, is 70 there. Then I'm going to go to do a truss analysis. I just made a video actually prior to this one. Do a method of joint analysis to calculate the member forces. Take out joint A. We go to joint A, we got 70 kips. And then we have this member, which is a tension, showing up. And this member is a compression. Always top member compression, bottom member tension in a situation like this. Then I want to find out the angle of this. The angle of this is easy. Alpha. Tangent of alpha is equal basically opposite. Divided by Jason, which is 12 divided by 36. So the alpha comes out 18.43. And we end up with this situation pretty easy. You do summation f of y, you have this, and you have that. And then you calculate this member. Then you do summation f of x. Now you have all information, and you calculate f of ab. So now we have that, but we're looking for this member. When I come back to this joint is right here, is a zero member, because summation f of y, there's nothing there. And this member is equal this member, so f of ab comes out f of bc, which becomes 210. So the tension force in this member is 210 kips. We're going to design it for that. I did the same exact thing in allowable stress design, come out to 150. But we get to that minute. So when we look at what I have on the screen, take a look at what I have on the screen. And when we look at the tension member, there's four different things we've got to worry about. Number one, when we have a member like this is a piece of steel. It's an angle iron. It could be I-shape, it could be channel, it could be anything. When we do a tension, we check for yielding. That means if I pull this apart, what force it will take to go beyond the yield force. And the yield force is a 36 KSI or 50 KSI, whatever it's going to be. That's one, and that's based on a cross-sectional area. Two is rupture. What if I got a hole in here, and this hole is connected to a gusset plate? Now, because I have a hole right in here, so the cross-section is weaker, is smaller, so that's a rupture. We check that. And the other two also, block shear, and then another thing we check for that, and also slenderness ratio, as I have on the screen. So we're going to go through those steps to figure these out. Then we're going to come back in here. We're going to have, on a low resistance factor design, we're going to calculate the yielding, which is given by this equation, P and Fy divided by Ag, but this really should be phi times Fy, and we're going to bring in, calculate the minimum Ag, which is 210, the force that we have, divided by 0.9, which is a phi t, times 36, and that is give us that cross-sectional area will satisfy the yielding. But what about rupture? We don't know how many holes we have there. We don't know. So at this point, we're going to say, okay, the minimum cross-sectional area is equal Pu divided by phi times FAU times U. FAU is, as you can see on the screen, we have a yield, but we know that if you pull the steel, it will break at FAU much later on than yield. Then time U, this is a factor, and plus estimated area of the hole, which we have to give estimate at this point. We're going to go into table D3 to calculate U. So we're going to, at this point, because we don't know what size of an angle do we have, we go into assume U is a 0.85. And equation U is basically, from that table, is 1 minus, case number 2, U is equal 1 minus x bar divided by L. X bar, we can find that once we have the size of the angle from the table. And L is the length between the first hole and the last hole. If I have 2 rows of hole connecting, then that's how long it will be. To understand this a little bit better, you can watch my previous video, which we designed the gusset plate for connection on the truss, actually. So we're going to go ahead and calculate minimum AG. Right now, that's where I am. And PU, which we say came out to 210. And divide that by phi for rupture is 0.75. Multiply FAU for is a 58. And then we have U, which is 0.85. Plus 4. Because it's a double angle, because I got a double angle right here, I got 2 holes here, and I got 2 holes on that side. So now the cross-sectional, this is one cross-sectional. So I got 2 holes here, 2 holes there, so I got to deduct 4 holes. So plus 4 times, we were told use 3/4 inch diameter bolt. So 3/4 inch, this is the diameter of the bolt diameter. Plus the hole size, we're going to give it another 1/8. Okay, to make it an area, we're going to assume the thickness of the plate, let's make it a 3/8. 3/8, and that's a plate thickness, the angled thickness. So all that come out, the minimum AG for rupture is going to come out. Oh, that's not good. Minimum AG. $6.99 inch squares. Obviously, it's bigger than that one. That's kind of good. And per code, we rather have our R should be all over 300, as we mentioned, for the slenderness. So that's equal basically, L is the length of this member, which is 12. So it's 12 times 12, and then divided by 300. And I have 0.48 inch. So now we have that. 2 from table 115 AISC 16th edition. We select select 2 angle. So I'm going to have 2 L5 by 5 by 3H thickness. Two L6 by 4 by 3/8. So we're going to preferably, in this kind of situation, it really works better if you use 2 angles. They're not the same length, one length, because it's easier when you put the bolt in, and it makes it workable. So from the table, for this one right here, we have area comes out to be, so from the table, as you can see on the screen, we have the area 722, x bar 0.993, and RY is equal to 161. For yielding, we have Pn equal Fy time Ag. In this case, we have 36 KSI time 7.22, and that is 259 kips, 259.9 kips. So now we have this size 259. This is a 5. And for load resistance factor design, it's going to be phi time PN, which is equal 0.9 times 259.9, and that's equal 233.9, and that's bigger than 210. So 233.9 keeps bigger than 210. So it passed this angle that we just picked out. It passed the yield for 210. And since we picked this one up, now we can switch it over to allowable stress design. Let me see if I have room here. So we're going to do allowable stress design right here. And omega is 0.67, again, for this one. And Pn divided by omega, which was Pn 259.9 divided by 1.67, and that's equal 155.6, which is bigger than 150 right there, and so that's okay. So now past that and yield, and let me erase this, we continue. We're going to do the rupture, and the equation we just had before the erase is U equal 1 minus x bar divided by L. X bar we got it from the table, and 0.993, and L is 8, basically is from the first bore hole to the last bore hole, which is 4 and 4, that's 8 inches. So now we have that, and then the next thing we're going to calculate the net area. Remember, we got to go ahead and right here, if I look at the cross section of the side, we got 2 holes and 1 plate and 1 angle, and 2 holes on the other angle, so there's 4 of them. So my net cross sectional area become, we know the total cross-sectional area was 722, and now I'm going to deduct minus 4 times 3/4 inch plus 1/8 times 3/8, okay? So that's basically diameter of the hole, and make the area times the thickness, and that comes out to be 5.91 inch square. This is from the book. So Pn is equal FEU U times AN. FEU is a 50 KSI time U came out to 0.883, and AN is a 591 and equal 302.7 kips. Okay, so now we have this. We can go ahead and we can do a load resistance factor design. A load resistance factor design. Phi for rupture is 0.75. And phi time Pn is equal 0.75 times 302.7, which is equal to 227, and that's bigger than I erased it, 210, which is this number in load resistance factor design. And in allowable stress design, we have our omega is equal to, and Pn divided by omega is equal 302.7 divided by 2 is equal 151.3, which is bigger than 150, and that's also okay in allowable stress design. So if you look at the slenderness ratio, L divided by R minimum, and our L was 12 times 12, and R came out to be 161. That's equal 89.4, which is less than 300. We met that also. Now we can say, okay, use 2 angle L 6 by 4 by 3/8. That will work. So one of the whole thing I want to explain before I finish it up is this 4 hole. You got 1, 2, 3, we got two lines of hole, and then we got two of them 4 apart, so our L is 8. But when we look at the cross-sectional area, because you got 2 angle iron and you got 2 hole, you got 2 hole in here, you got 2 hole in there, and when you put them together, the entire thing act as a 1 unit. So now I got to deduct 4 hole, because this area is all these 2 combined. All right, I hope you like this, and if you like it, please give it a thumbs up. Have a good day.